morning. So today we are going to continue on this model 5. So in this, so far we have our discussions focus on how to interface IO devices with the CPU, and in that we have completed discussion on programmed IO. So programmed IO, CPU has to check device after device whether they are ready or not. Once they are ready, they can interact with the CPU. Okay, so it's a low efficiency technique. So we go for interrupt-driven IO. So in interrupt-driven IO, whenever the devices are ready, it is the responsibility or duty of the IO interface to inform the CPU that the device is ready or devices are ready. So that kind of information will come from the IO interface to the CPU. And upon receiving that signal from the IO interface, CPU will understand the devices are ready and it can have interaction with the selected device. Okay, right. Now, I touched upon the multiple interrupts. When interrupts are from all the IO interfaces in a design, we have multiple IO devices, multiple IO interface. If the interrupt signals are coming from all the IO interface, in that case, how it can be tackled by the processor. So this is what we are going to discuss. So the idea is how to identify which model has caused interrupt, and when multiple devices are interrupting the CPU at a time, how it can be addressed. So this is what we have to we are going to discuss. But this also is started in previous class. I told you 8259 is a processor. It's a peripheral interface controller, peripheral interrupt controller, and we are using 8259 to get this thing solved. But let's see other options. Okay, apart from interrupt handler. Okay, so one simple approach is we can allot one interrupt signal for one IO interface. Okay, so it means, for example, we have a processor. Then we have, let us assume, three IO interfaces. IO1, IO2, and IO3, something like this. So they may have devices, device 1, device 2. It may have only one device, say device 1. It may have a couple of devices. Just for example, okay, let it be. We are not bothering about how many devices in this. So we are only bothering about how the multiple IO interface can be connected to CPU through interrupt. So what we can do, we can allot one pin from CPU to one IO interface. So this is nothing but interrupt for device 1. This is interrupt line for device 2, and this is interrupt line for device 3, something like this. Okay, right? Now CPU will approach the devices. With interrupt with a request. So CPU separately approach the devices by sending a request. I want to talk to device 1 of yours. Like that, it will send a request. Then CPU may be engaged with some other work. This is CPU. So whenever the particular device in that particular interface is ready, it can send in its exclusive line. So this is what different line for each model. So for every model we have one interrupt pin we can allot. So this way we can solve. Okay, this is one aspect. But here the thing is the number of pins. See, we should dedicate some pins for interrupt purpose. So that issue is there. We cannot use those pins for some other purpose. So they are all allotted for only interrupt related activities. Okay, so nowadays if you take processors are comes with multi-functioning options. In every pin, they are able to do multi-function. So they are not made for exclusive functions. So they are made for multiple functions. But interrupt related pins, mostly they will not engage multiple functions on these pins. So they are all only for exclusive functions. So say for example IO device 1 is connected to INT1. Whether the IO device 1 is ready or not, this pin we cannot use for some other purpose. So it is dedicated for that particular device. Like this pin dedicated for this device, this pin dedicated for this device. So this is the flaw in this kind of approach. Okay, right. So this is one aspect. This point is clear. And again, suppose we have only 3 pins, for example, in our CPU for interrupt. It means we can connect only 3 interfaces. We cannot connect 4th interface. We want to have 4th interface. We cannot do in this way. We cannot do in this way. This point is clear. Any issues in understanding this point? Okay, right. What is the second option? Software polling. So here the device request may be sent to all the interface. Device interface may be sent to all the devices separately, but we have one common interrupt line. One common interrupt line. So whichever IO interface wants to send interrupt signal to the CPU, we have only one pin allotted for allotted for interrupt. So whichever device wants to send interrupt signal, it can use the common line. Okay, right. In that case, when interrupt comes, CPU has to check whether the interrupt is due to this device or whether the interrupt is due to this device or interrupt is due to this device. Now, how to do this? So this is called software polling. Polling means what? Checking one after other. So this is what software polling. So how it can do this, that we will see. Okay, but this kind of activity is very slow because CPU gets interrupt because of this interface. Let us assume IO3 sent interrupt signal to the CPU, but CPU does not aware it is coming from IO3. So what it will do? It will check first IO1, then it will check IO2, then it will check IO3, then it will understand, yes, IO3 was the device which sent interrupt, so it can engage with that. But it's a slow process. So here we can have n number of devices because only one line we are connecting. No, we are not restricted with the number of pins. We are using only one pin. We can connect n number of devices. But if the nth device is ready, it has to wait for CPU to come to its place. I mean, it has to wait for its turn. So that issue is there in this software polling. So please understand this concept. The earlier concept, one interrupt line we are alerting for one IO interface. So whoever ready, they can send a signal to the CPU, and CPU in turn will understand it's coming from this device, right? So directly it can interact with that device. Fine. But the problem is we have limitation. We cannot connect n number of devices. How many pins we have in our CPU? That many, I mean, how many pins are dedicated for interrupt? Only those pins we can use for this connection. Okay. The second option is we can use only one pin for interrupt and we can connect n number of devices whoever in that device, whoever in that interrupt connection ready, they can send interrupt signal to the CPU. Now again CPU has to check interrupt one after other whether the interrupt is due to that particular interface or not. So it has to check. So this is called software polling. It's a slow process. Okay, so this is again there are two ways. Okay, so this software poll can be carried out by daisy chain. By daisy chain method, I'll tell you what is called daisy chain by seeing this, by taking this diagram. Look here, there are three devices. For example, like that we have a number of devices. All the devices have common interrupt request. So the devices may have, I mean, here instead of device, you can take it as IO interface, and there are devices connected to every IO interface. Those things are not shown just for the sake of simplicity. Okay, right. Whenever the interrupt comes, if any of these IO interface is ready, it can send an interrupt signal to the CPU. It can send this interrupt signal to the CPU. Now CPU will go to the first device. Usually the first device will be high priority device. Usually the first device will be high priority device, and the next priority will be given to device 2. The lowest priority will be given to the one which is connected as this side. Okay, so like this they can connect the daisy chain. The daisy is a flower name. The petals of the flower will be like this. So one after other, one after other, one after other. Okay, so it has the diagram resembles daisy flower. That's why it's called daisy chain. Okay, so here the high priority device is kept, and here the low priority device is kept. Whenever interrupt comes from any of these three devices, CPU will send interrupt acknowledgement. It will ask whether the request comes from you. Okay, in case if the device gets interrupt acknowledgement, it will send one more information, its address. Suppose 00 is its address. Let us assume 00 is the address, 01 is the address, 1011 is the address. For example, whenever the device is whenever the IO interface is sending interrupt, CPU will send common acknowledgement to all the devices. But the acknowledgement will go to the high priority device. If this device was the interrupted device, then it will send 00 to the same line again. So upon receiving 00, CPU will understand that the interrupt request came from this device. So it will attend that device. Suppose the interrupt request was from device 3, that is IO interface 3. Then what will happen? This device will forward that interrupt acknowledgement to the device 2. Device 2 will forward the interrupt acknowledgement to the device 3. Now device 3 will send 11 because its address to the CPU. So CPU will understand the interrupt was interrupt raised by this device, so it can directly have interaction with that device. So this is the way the multiple devices can be connected to CPU. Suppose here device 1 is ready, device 3 is also ready, right? So let us assume first the device 3 sends signal to the CPU. Before the acknowledgement comes from CPU, before interrupt acknowledgement comes from CPU, let us assume device 1 is ready, and it will send signal to the CPU. Okay, right. Now interrupt acknowledgement will come, right? Interrupt acknowledgement will come. So device 1 will say, I was the one interrupted you. So this device 3 will not get its attention till the device 1 related things are over. I repeat again, this is a high priority interrupt, high priority IO interface, low priority interrupt IO interface. In the daisy chain, the outer pedals contains high priority devices. The inner pedals contains low priority. Okay, right. So first this interface was ready. So it has initiated interrupt signal to the CPU. For every interrupt signal, CPU will send interrupt acknowledgement. When the interrupt acknowledgement is while the interrupt acknowledgement is generating, let us assume device 1 is ready. So when the interrupt acknowledgement comes from CPU, this device assumes the interrupt acknowledgement is for its request. So it will send 00 first. So CPU will have interaction with the device 1. Once all the interactions are over, then this device can forward the interrupt acknowledgement to here. This will forward to here. During that time, if device 3 still wants to communicate to CPU, then it will send 11. And CPU will now understand this is also requiring attention, so it will go to that device and it will function. So this is the way the daisy chain is working. This point is clear. So high priority interrupt can override low priority interrupt. So it is up to the users to keep which are the devices with high priority, which are the devices low priority. So in the chain, the outer link should have high priority devices and the inner links must have low priority devices. Accordingly, we have to rearrange. In case if we feel we want to change the order, we have to reconnect the IO devices. So daisy chain is clear. Any problem in understanding this? Okay, thank you. Right. Now, sometimes we may be thinking we want to have device 3 with high priority. Okay, this the another way is there. So this is the way it's working. There is one more way. Bus master. So bus master concept, that is another concept. Like daisy chain, the second concept is bus master concept. Okay. So what is the idea? The idea is we have CPU, we have device, IO interface 1, IO interface 2, IO interface 3. Okay, right. They are all connected to a common interrupt signal. They are all connected to common interrupt signal, right? So here it is not like a priority or something. So here, whichever device wants to interrupt, so what it will do, it will take control of this bus. Suppose IO3 wants to send interrupt signal to CPU. So before that, it will take control of this bus. So it may intimate the other IO devices. I am going to use this bus. I'm going to use this bus. So please don't interrupt. So that kind of intimation can be forwarded to other devices, and this device will take the bus and it will send interrupt signal. After that, CPU can have interaction with the IO3 through its data bus. So I'll list down the steps. So whichever device wants to raise interrupt, for example, if IO3 wants to raise interrupt, if IO3 wants to raise interrupt, then it will take the control of bus and intimate other devices. Okay. So, in recent days, not intimating other devices along with how long it is going to use. So that information also will be forwarded to other devices. So till that time, the other devices cannot send interrupt signal to the CPU. Okay, so this is second scheme. So daisy chain or bus master are the two options we have when we have only one interrupt line in our CPU. Okay, so the conclusion is we have two things. One is CPU with one interrupt line for one IO model. One interrupt line for one IO model. So whoever wants to talk to CPU, they can send interrupt signal, and CPU can come to the can attend the IO devices. But the issue is we are restricted with the number of pins we have. Suppose we have only 3 pins, then we can connect only 3 interfaces. So the solution is we can have only one pin. We can have only one pin as the interrupt pin, but multiple devices can be connected. Multiple devices can be connected. In that case, we have two options. Option number one, either we can use daisy chain or we can use bus master approach. So what is the thing in daisy chain? In both the cases, only one operation. Whichever device wants to send interrupt, they have to send interrupt signal to the CPU. Now, how CPU is locating a particular device? In that aspect, daisy chain and bus master are different. So here, in the daisy chain, the interrupt acknowledgement will come from the CPU, device after device. And whichever device initiated the interrupt, they will respond to this acknowledgement with one more, like its address, so that CPU will understand which device interrupted. So it will just go to the device and it will engage with the device. Whereas in the bus master approach, whichever device wants to send an interrupt, it can take control of the bus and it will initiate interrupt. Then it will complete interaction with the CPU. Then it releases the bus. So here no priority kind of thing. So here it is like whoever wants to talk, they can take a control, engage, release. So by these two ways, interrupts are handled in computer organization. So I hope I have clarified the points. Anybody having doubts, please let me know. We'll complete this interrupt concept by today. So shall I move to new topic? So we discussed in detail what is called interrupt, why we need interrupt, because programmed IO is a low efficient approach, so we go for interrupt concept. In the interrupt, it's high efficiency, but it requires some extra thing in the form of software or in the form of hardware to tackle issues. But interrupt is better than programmed IO from utilization point of view. We are replacing CPU much better compared to normal programmed IO. Okay, right. Okay, I'll just start this topic, what is called direct memory access. Then, in detail, we will discuss in the next class. Right. So far, in our discussions, whether interrupt-driven IO or programmed IO, what's the problem is, or what's the way they are communicating is, say, for example, we have a CPU, we have a CPU, we have IO interface, we have main memory. For example, for the sake of again simplicity, I am not using cache memory, disk memory and all. I am just using only this, right? And in the IO interface, one device is connected. Now, this device has some bulk amount of data. Okay, first let us take normal data, then we will go for bulk data. Suppose this device wants to store some data into the memory. So the device has some data, it wants to store that data into this memory. Okay, right. Now what will happen? This device will send the data to the IO interface. In the IO interface, we have a data register. So the data will go to the data register of IO interface. From then it will come to CPU. In CPU we have a register, say accumulator kind of thing. So it will be loaded here. Then it will be going to memory in a particular location and the data will be stored. I repeat again. The device wants to send a data. So first it will send the data to the IO interface. The IO interface, we have a data register. In that first the data will be stored. Then the stored data will be sent to CPU. The CPU, we have a register, say accumulator or some special registers. They will collect the data from the IO interface. Then it will be forwarded to the memory. Okay, right. Suppose this, okay, this is the data path. Suppose this device wants to store 1 kilobyte of data into this memory. So again, this 1 kilobyte of data is divided into portion of data. Data 1, data 2. Let us assume it is an 8-bit processor. So data 1, data 2, data 1000. So every data will be of 1 byte. Every data will be of 1 byte. So the first data from the device 1 will follow this way. Second data will follow this way. Third data. So up to 1000 data, this is the way the process will happen. Okay, right. Suppose 1 megabyte of data. Again, it is divided into that many portions. So byte after byte, the data will be sent to the main memory. So this is what happening in programmed IO, interrupt IO. In both the cases, whenever IO device wants to talk to a memory, it has to talk through CPU. It has to use CPU in the communication path. So what's the problem? The problem is, suppose 1000 data to be stored from this place to this place. What is the role CPU is doing here? It is acting like a mediator. It is collecting and forwarding, collecting and forwarding. So till this 1000 data transmission completes, we cannot use accumulator for any other purpose in our program, right? So this accumulator or some register, some special register, we cannot use for any other purpose. So CPU has to wait till completing all this 1000 byte of data to transfer from this place to this place. CPU is nothing to do with these data. It is not going to operate on these data. It is just collecting and forwarding, collecting and forwarding. So CPU, it is something like we are CPU is not able to utilize this register. It is something like CPU is not working properly. CPU is not working with its full efficiency, because for to take this register back, it has to wait to complete this 1000 data to reach the memory. So till that time, CPU cannot use this register. So we are wasting the efficiency of the CPU, because we are waiting. We are asking the CPU to wait for this unnecessary data transfer delay. So a new development has come. The devices, whenever they want to talk to main memory, they can directly talk to main memory without interfering CPU. 1000 data it wants to transfer, it can directly transfer. So directly the devices can access the memory. That's why this scheme is called direct memory access. Listen carefully. This direct memory access is useful only when the devices wants to talk to main memory, or main memory vice versa, main memory to devices. Suppose some bulk amount of data to be printed. Okay, so it can directly send to the printer, rather forwarding that to the CPU to the printer. It can directly send to the printer, something like this. Okay, so whenever devices wants to communicate memory, or vice versa, memory wants to communicate devices, then they can talk each other in a direct link. By doing so, we are not disturbing the CPU. We are not disturbing a particular register in a CPU. We are increasing efficiency of the CPU. So CPU can be engaged with something else. Let the data transfer is taking place between these two. CPU may be doing something else. When the data transfer is over, it will intimate the CPU, yes, we have completed. Then CPU can engage with either memory or devices. So by doing this, we are increasing the efficiency of the system. So this is called direct memory access. So without involving the processor, devices can directly talk to memory, or memory can directly talk to devices, and this scheme is called as direct memory access. Okay, right. So to implement the direct memory access, what are the steps to take? Number one, we need a direct memory access controller. We need a controller, direct memory access controller. Second, this direct memory access controller should send a request, bus request to CPU, because this direct memory access control will not have any address bus data bus. In an overall computer organization system, CPU is the master. CPU is holding all the control. CPU is having address bus data bus. Okay, so DMA controller is like agent. That fellow will not have address bus or data bus. So it has to send a bus request to the CPU. CPU will grant the bus. CPU grant the request. Bus request will be granted by the CPU. Fourth, DMA controller takes control over the bus and do data transfer. during this time, CPU may be engaged with other work. When DMA controller completes the operation, it will hand over the bus to CPU. That's all. These are the sequence of operations we need to have. Okay, so to implement direct memory access, we need direct memory access controller. It is nothing but another IC, another chip, and this chip is connected between IO devices and memory, and some signals are connected between DMA control and CPU. So whenever the IO devices wants to send some bulk amount of data to the memory, it will approach the DMA controller. DMA controller will send a request to the CPU to take the bus, address bus, data bus, and control bus of CPU. It will send a request, then it will take the bus, and it will by using this bus, it able to transmit data to the memory. Once the transmission is over, it can hand over the bus back to CPU. So while DMA is happening, CPU is not kept idle. It can be asked to do some other operation which does not require bus. So by doing so, we are not interfering CPU in this useless transmission, because from CPU point of view it's useless, because it is nothing to do with the data. Okay, so from CPU point of view it's useless. So CPU may be engaged with some other work. So we are increasing the efficiency by using DMA concept. Okay, so any doubt in this? Okay, so I will stop at this point. Next class we are going to discuss in detail about DMA controller, how it looks like. Okay, so that we are going to discuss in detail. So I will stop at this point. So what are the things we discussed? So whenever we want to connect interrupt with multiple devices, what are the options? We have a dedicated pins on which we can have devices, but it has a problem. We can have only minimum number of interface with the CPU. If you want to have more number of components to be connected with CPU, we have to go for either daisy chain or bus master approach. In both the cases, we have only one interrupt line on which all the devices can be connected. Whenever the device wants to send interrupt, they can use the common line and they can send. How CPU interpreting? That way, daisy chain and bus master controller are differing. Then, whenever we want to transfer bulk amount of data, bulk means it varies system to system. For some system, 1K itself bulk. For some system, 1 mega is bulk. For that system, 1K is normal. Okay, so it's very difficult to tell which is called bulk. Okay, so whenever a bulk amount of data to transfer, then the devices need not to interfere, need not to pass through CPU. Rather, it can just bypass the CPU in this transmission. Directly they can access the memory. But to do that, we need a DMA controller, and DMA controller will interact with CPU to take the bus, and using that bus, it can transmit the data from device to memory or memory to device. After that, it can hand over the bus back to CPU. So during the DMA operation, CPU is engaged with some other work, so that overall efficiency will be improved. Okay, so that's all about this discussion. So we will continue on DMA control in the next class also. So let me just stop recording.